What if your database had no boss node, no single leader, and still never lost your data? That's leaderless replication, and here's the mechanic that makes it work. In the classic setup, the client talks to one node, and if that node is slower down, you're stuck waiting. Leaderless flips this. The client sends every write to ALL the replicas at once. The write is considered done the moment a majority of nodes shout back, "Got it." Slow nodes, dead nodes, whatever, they never block you because the majority already answered. Reads work the same way. The client asks all the replicas and decides the value once enough of them respond. This idea was popularized by Amazon's Dynamo paper, Cassandra and colleagues, back in 2007. It inspired real systems you've heard of, Cassandra and React. And its deeper roots go back to Gifford's weighted voting for replicated data from 1979. Let's make it concrete with 5 replicas, N1 through N5, storing one user's shopping cart. Right now, every node holds the same cart, just shoes. The user adds a hat, so the client writes shoes, hat to all 5 nodes. All 5 acknowledge, a read later asks everyone, the majority says shoes, hat, and life is good. But now, watch what happens when nodes drop. The user adds the hat again, but this time, N4 and N5 are down. Only N1, N2, and N3 acknowledge, that's 3 out of 5, still a majority, so the write succeeds. Time passes, and a read comes in. But now N2 and N3 are offline, and N4 and N5 have come back still holding the old shoes. So the responders are N1 saying shoes, hat, and N4, and N5 both saying just shoes. Naive majority, 2 votes for shoes, 1 for shoes, hat. The hat vanishes. That's flat out wrong, and counting votes will never fix it. The fix is version numbers. Every write gets tagged with a version. The original shoes is version 1, and shoes, hat is version 2. On a read, the client waits for a quorum of responses, then picks the value with the newest version, even if only own node has it. So version 2 beats the 2 version 1s, the hat comes back, and the card is correct. But we still have stale nodes out there holding old data, and there are 3 ways to heal them. First, read repair. When the client sees a node return a stale value, it writes the fresh value straight back to it. Second, hinted handoff. While a node is down, a healthy node temporarily holds its writes and delivers them once it recovers, like a neighbor signing for your package and giving it once you're back home. Third, anti-entropy, a background process where nodes compare nodes and sync up whatever they missed, quietly and later. Now the last piece, that majority number doesn't have to be a majority, you can tune it. Call N the total replicas, W the nodes that must acknowledge a write, and R the nodes that must respond to a read. The golden rule is W plus R greater than N. That overlap guarantees at least one node in every read also saw the latest write, so a fresh copy is always in the room. With 5 nodes, balance means W equals 3 and R equals 3. 3 plus 3 is 6, greater than 5, so it holds. Got a write-heavy app? Set W to 1 and R to 5. Writes finish the instant one node acts, and reads check everyone to stay correct. Read-heavy instead. Flip it, W equals 5, R equals 1. Every write hits all nodes, so any single read is guaranteed fresh. Same overlap rule, different trade-off, tuned to your workload. So leaderless replication trades a single leader for high availability plus tunable version-aware consistency. No boss node, no single point of failure, and your data never quietly disappears again. If you like this video, please give a thumbs up. Share it with your friends preparing for system design interviews. Subscribe to learn deep software engineering concepts.